Hello, everybody, and welcome to the Speak Sets online webinar. My name is Shraddha Menon. Before we get started with today's session, we would just like to thank our sponsorship from IAS, which allows us to offer all these resources free of charge. So make sure and check out our website for more info on upcoming events and meetings and to see everything available for the community. Today's talk is by Ricarda Gatter, an early stage researcher in the European Training Network SLATE at the Center for Marine Environmental Sciences at the University of Bremen under the supervision of Dr. Catherine Hun and Dr. Michael Clare. She completed a master's from the University of College London, after which she pursued a PhD in marine geosciences. Her PhD topic focused on the investigation of failure planes of submarine landslides and aimed to understand the material in which the submarine landslides initiated. She was also the recipient of the 2019 Outstanding Poster and the PICO Award for the poster titled The Significance of Weak Layers for Submarine Slope Failure. Her other specializations include computer tomography and geotechnical analysis. In today's talk, she'll provide insights on the controls in submarine landslide formation, focusing on the key roles of sediment structure and composition on the weak layers within the slope stratigraphy. And with this, I pass on the forum to you. Over to you.
Thank you very much. And thank you very much for having me. It is a delight to give this talk today in the frame of the SETS online webinar. And as Shraddha already told you, I'll be talking a little bit about submarine landslides, in particular, the controls on submarine landslide formation. So why do we even want to know something about submarine landslides? Let's see. And of course, my presentation is not working. 1 second. Ah, no, it's working. Okay, sorry for that. So submarine landslides can be found virtually all over the world, on all continental margins, but also in fjords, in river systems, and so on. And one of the maybe best known submarine landslides is the Storegga slide. The Storegga slide occurred about 8,000 years ago offshore Norway, and it removed over 3,500 cubic kilometers of sediment and generated a huge tsunami that had wave heights of over 20 meters in comparison to the sea level at the time. Another very well-known example is the Grand Banks event from 1929. This event is well known because not only was a slump triggered by an earthquake, but there was also a turbidity current, which then caused ruptures in the seafloor telecommunication cables, even 500 kilometers from the actual source of the submarine landslide. However, it's not only these very large events that have big social and economic consequences, also smaller landslides can have a big impact. For example, the Nice airport slide in 1979, it's a comparatively small event. However, it caused partly destruction of the harbor constructions, as well as a tsunami with a wave height of 2 to 3 meters and also some human death. So the question behind all of these events is actually, well, what causes submarine landslides? So what causes submarine slopes to destabilize? And this can be very good explained by the factor of safety. And the factor of safety is a function of the resisting forces, which actually stabilize the slope, which is mainly the shear strength of the sediment, which in turn is a function of the sediment's coefficient of friction, the sediment's cohesion, but also the overburden stress and then pore pressure. And against these resisting forces act the driving forces, mainly the slope angle. And a slope will destabilize if the driving forces exceed the resisting forces. And now there are different mechanisms and factors that can influence this function. So either by increasing the driving forces or by decreasing the resisting forces. The most common factor or the most discussed factor are actually earthquakes. Earthquakes can cause an increase in the slope angle, but also an increase in pore pressure thereby causing slope failure. Another mechanism that can cause the increase of the slope angle is, for example, tectonic activity. But an decrease in slope angle can also be found due to volcanic activity. In this case, there might also be a change in the shear strength of the sediment, mainly because of the magma chamber, which can cause some compressional strength reduction or increases. Then another important factor are gas hydrates. In this case, gas hydrate dissociation can cause an increase in pore pressure, but it can also change the shear strength of the sediment. And another example of pore pressure increase would be wave loading or sea level change. So these are all summarized as so-called triggering mechanisms. So they're usually rather short-term changes. However, they can all be kind of summarized in one thing, which is the slope stratigraphy. Because depending on the slope stratigraphy, we have specific shear strengths, we have specific pore pressure. And here we often talk about specific layers that are weaker than the surrounding sediments. And it's these weak layers along which failure first initiates. And this is what I'm mainly going to talk about throughout this talk, which is the weak layer concept, which means the weak layer is characterized by a shear reduction and thereby causes slope failure. The weak layer concept has been around for quite a while, and in 2014, Lockhart et al. Tried to characterize weak layers in terms of their geotechnical behavior. So first, what they found was the development of weak layers due to strain softening. If we look at a clay layer, for example, here you can see sketched some clay particles. And if now failure occurs, so T0 is the state before failure, and then T1 would be the state after failure. And what you can see, what is caused by strain softening is a realignment of the particles, which causes a reduction in the shear strength, thereby causing failure. Another mechanism is liquefaction. In this case, we usually look at a sediment sequence, for example, underlying sand overlaid by clay. Again, T0 is the time before failure. If we now have failure, what happens is due to, for example, an earthquake, we have a pore pressure increase, which can push apart particles and thereby reduce the shear strength of the sediment. Another mechanism would be water film formation. In this case, we again have coarse-grained sediment overlain by fine-grained sediment, and due to failure, this coarse-grained sediment, or during failure, this coarse-grained sediment can either break or rearrange, and the pore fluids will then move up from the underlying coarse-grained sediment and then be basically stuck underneath the fine-grained sediment. And failure will then, what you can imagine is this fine-grained sediment and sliding on top of this water film. So the main hypothesis here is that the slope stratigraphy plays a critical role in submarine landslide formation. And this is because slope stratigraphy controls what kind of weak layer can be found, and also the mechanism of how a weak layer can be formed. And the main question I addressed was, well, what do we actually know about weak layers? What do we know in terms of their composition and their structure? And then also, how can we test this weak layer concept? And the main aim was to find out more about the structure and the composition of weak layers, both qualitatively and quantitatively, and see how these findings will affect our understanding of the weak layer concept. To do this, I first compiled a new global landslide catalog. This catalog included 64 case studies from published literature. And I only included case studies for which, first of all, the head wall could be identified, and then also for which the basal surface, so the failure plane or glide plane, could be identified. And what I found was, well, 64 case studies, and we wanted to know, okay, what can we learn from these 64 case studies? And the first thing I wanted to know was which methods have been used to analyze these case studies. So which methods were used to, first of all, identify, for example, failure planes, but also to make assumptions about potential weak layers. And what I found was that not even half of these landslide case studies sampled relevant sediments. What do I mean with relevant sediments? It means the sediments in which failure occurred. So the weak layer sediments or the failure plane sediments. So there are no core materials, and there is also no in situ measurements available for 38 out of the 64 case studies. Nevertheless, we went one step further and checked, okay, for the case studies where we have sediment cores or in situ measurements, where were these cores and in situ measurements taken from? Were they taken inside the actual slide area, or were they taken outside the slide area? And what you can see here is that almost half of these case studies only had sediment cores and in situ measurements available from inside the landslide. Why is this important? Because as you can imagine, once the slide happened, it actually removes material, it destroys some of the sediment structure. So if we only have sediment cores and in situ measurements that were taken from inside the slide area, it is very hard to then go back and find out what was the original weak layer. However, there were also 7 case studies with sediment cores and in situ measurements outside the slide area, and then ideally the ideal case where you have both information from inside and outside the slide area. So we can summarize that, well, sediment cores are very scarce. However, these are really crucial in order to investigate weak layers. This is limited information. However, again, we decided, well, what can we infer from these studies? And what I tried to do was classify weak layers, and that is classify them in terms of their lithologies. And what I found was 4 main lithology groups. So one is weak layers related to only clay layers. Another is weak layers related to siliciclastic sediment sequences. So for example, a sand clay sequence. And then volcaniclastic sediment sequences, for example, tephra and clay. And then fossiliferous sediment sequences, for example, diatoms and clay. And as you can see, the majority of the until now found weak layers are related to siliciclastic sediment sequences. And this shows that that actually it's not only a layer that is important, but usually we talk about distinct lithological contrasts, which together control then the formation of a weak layer, and therefore also dictate where failure planes form and where submarine landslides will form. So if we now go back to our weak layer concept, we see that, well, clay layers are typically associated with, for example, sensitive clays are typically associated with strain softening. Siliciclastic sediment sequences will be more associated with liquefaction. And then volcaniclastic and fossiliferous sediment sequences will be more related to this water film formation. This is important because it shows that if we manage to identify the lithology of a weak layer, we can then think about what might actually trigger landslides. So, for example, in the case of liquefaction, we assume that an earthquake may trigger the landslide, while in other cases, gas hydrate dissolution may be more important, and so on. The other important fact is that if we identify the lithology, we can also associate these lithologies to specific environments. For example, sensitive clays are very common in fjords. Siliciclastic sediment sequences, well, they're found all over, but are very common active margins and tectonic activity settings. While volcanic clastic sediments you will find around volcanic islands, for example, and then upwelling regions will be characterized by fossiliferous sediment sequences. So it really shows that although there are various processes involved in this weak layer formation, the type and distribution of weak layers is actually controlled by the environment. So what do we know about weak layers until now? Well, we've seen that weak layers are basically controlled by distinct lithological interfaces. We've also seen that there are many processes involved in weak layer formation, but that they are associated to very specific environments. So these two statements we found out by pure literature research. So what can we do to actually test this weak layer concept? For this, we need sample material from the actual weak layer. So we need sediment cores, we need an accurate identification, and also careful sampling. So what I want to show you in the second part of the talk is how we actually can test this concept by means of two case studies. And the first case study I'd like to introduce you to is the Athens slide. The Athens slide is located offshore Scotland. Offshore Scotland. It's a 4-stage retrogressive landslide. And what you can see here is a seismic line. Here's the head wall, and then the seismic line goes from here to here. So don't be confused. This point is here. And as you can see, it's a retrogressive slide, which means first this part failed, and then it retrogressed upslope, and this part failed. And this slide was chosen because we have cores available from the landslide. And especially we have this core number 4, which appears to sample the sediments which are equivalent to this stage 1 failure plane, as you can see from this dotted line. And what we did was we used fairly common analytical methods, core scanning methods, to investigate the sediment core. So this is a stratigraphy of the sediment core. What you can see here, the clay is in gray, then this greenish is silt, and then here in yellow sand material. And this is from a purely visual core description. And then the first analysis method we used was geophysical data, which is obtained from multi-sensor core logging. And you can see here the P-wave velocity, gamma ray density, fractional porosity, electrical resistivity, and magnetic susceptibility. And all of these datasets show a very distinct change in physical properties at around 7.3 meters. This indicates a very abrupt change in lithology and actually matches very well with the failure plane that was outlined from the seismic data. However, if we look more closely at, for example, P-wave velocity or gamma ray density, these values seem to be slightly off and seem to indicate a disturbance of the sediments. So where could such a disturbance come from? If we go back to the previous image of our seismic line, we see that core number 4 was taken downslope of the actual failure plane. And it appears that the failure plane actually steps up here. So the sediment, which was here evacuated, ramped up on top here before running out. And it could be that this ramping up caused a compression of this area and could thereby explain the slightly, for example, higher given velocity or gamma ray density. So the question is our distinct change then really linked to lithology and linked to a failure plane formation, or is it linked to this specific aspect? So therefore, we introduced another set of data, which was obtained from X-ray fluorescence. And what we can see that also in the geochemical data, we see this distinct change, which appears to correspond to similar depth as the change we saw in the geophysical data. So we can now say that our distinct change, our step change, is really related to a lithological contrast. However, now we wonder, could the failure plane also be lying further down in the sediment core? Because also here we see a slight change in most of the data sets. And again, we introduced another set of methods and another set of data, which is geotechnical data, in this case, water content, and then fall cone data. And especially the water content confirmed that our failure plane very likely correlates to this very distinct change in lithology. We therefore inferred our weak layer to be this clay sand sequence. This case study also showed us that we really needed this multidisciplinary approach to be sure and to be able to identify our weak layer. If we had only used one data set alone, there would have been far too many options of a possible weak layer. And again, what we have shown is that apparently it is really this lithological contrast that controls weak layer formation. Nevertheless, we wonder, why did failure initiate at this specific depth? Because lithological contrasts can be observed throughout the entire sediment course, here, here, or here. However, our standard test, our standard sedimentological analysis, as well as geotechnical methods, appear to be insufficient to actually understand why failure initiates at a specific depth. So we need to introduce new methodologies. And the one I personally used is microcomputed tomography. And I used the second case study to try and see what can be learned from these specific methods. So I will now introduce you to a second case study, and this is a work in preparation, but I'd like to just show you some first results and some first information we really gathered from this kind of data. So we now switch to the Finneidfjord slide. The Finneidfjord slide is located offshore Norway. It is also a fairly small landslide. However, it actually retrogressed onshore and thereby destroyed parts of the highway there. And it is a very well studied landslide. There's a lot of data available, which made it useful for us because we could really compare our new methodology with the already available data outside. So in this case, we have a sediment core outside the landslide, as you can see here. And I only show you a section of the sediment core, which is the section in which the actual weak layer was identified in. And the weak layer consists of a clay sand clay sequence embedded in background sediment, which basically consists of clay silt. And we took micro-CT samples from different layers, so from every unit of this weak layer, and then also a reference point from the background sediment. So what is micro-CT? Micro-CT or microcomputed tomography is a high-resolution, non-destructive imaging technique that allows you to look basically inside an object by using X-rays. So different materials have different densities and therefore X-ray attenuation, which can be used to reconstruct the object in 3D. So the way this works is that you have a light source, and the light source and then the light transmits through the sample, is collected by the detector, and that is done various times. So basically, you have your sample here, you get your image, then you rotate your sample, you get another image, you rotate your sample until you reach 180 degrees. And then all of these images are reconstructed into cross-sectional images, which can in turn then be reconstructed into a 3D volume that represents your internal structure of the sediment or of your sample. And this is really important and interesting because it can then be used to really analyze the 3D structure of the sediment, the grain distribution, but not only the distribution, also the orientation. Same goes for the pore distribution. You can analyze the pore connectivity, the pore orientation, and also the permeability of sediment fabric. And what I focused on is mainly the pore distribution. So this is what such a sediment 3D cube looks like. It's basically a grayscale image or 3D cube. The first thing you want to do is to segment this image, which basically means you want to segment it different phases. You want to say, okay, this is a grain, this is a pore. And what I usually do is I select 3 phases, which are the pore phase. Here in colors, you can see pores that are connected. So in this case, most of the pore space here in blue is connected. Well, then you have some separate smaller pores in all these other colors. Then a solid phase, in this case here shown in purple. And then also mixed phase. The mixed phase comes from resolution problems because it contains water and very, very fine-grained material that you cannot separate anymore. And the problem is that this water and this very fine-grained material basically has the same grayscale. And so we summarize it as one mixed phase. And we use these 3 phases now to, for example, approximate porosity. How do we approximate porosity? In this by calculating the pore phase or adding the pore phase and the mixed phase. This gives us an approximation of the porosity of this very specific sample. So if we now go back to our sediment core section, what we see here, these empty circles show only the pore phase, and then these filled circles show the pore phase plus the mixed phase. And we can already see quite big changes in the porosity between these different layers. However, you may wonder, well, we also see this from, for example, from the fractional porosity. Why do we have to do microscopy? So the additional information we get is, for example, porosity change within the sample. So if we, for example, look at this sample A3, which is taken from the upper sand, we can see here the pore phase, here the pore phase plus the mixed phase, and here the solid phase. And we can see that it varies greatly throughout the entire sample. This has implications. Which implications? First of all, it may have implications for permeability, for directional permeability, as permeability might be higher in the lower part of your sample than in the upper part of the sample, or it may be higher, lower, vertically and horizontally. And it also shows that the pores may not be distributed throughout the sample in the same way. And we can start and ask ourselves, well, what does the pore structure of each sample then actually look like? So now I've turned the sediment core. This is the lower part, this is the upper part. And we can start and look in 3D at the actual structure of our pore distribution. Here, for example, every single color again represents an individual pore space. And then here the colors are the same as the colors down here. And then in gray, I showed the mixed phase. And we can see that in this very fine material, there is only a very small percentage in this distinctive pores, while if we add the mixed phase, so this water fine-grained mix, we actually come to almost 46% of porosity. If we compare this now to our coarser grained samples, we can see that already the very distinctive pores make up a higher percentage. Interestingly though, the total porosity appears to be smaller. We can also see that although these samples were taken from the sand layer, both of these samples appear to look very, very different. And then we can also look at this upper clay and then the background sediment. And what I want to point out here is both of these samples were taken from clay that visually looked the same. However, if we now look at the microscale, we can see that this upper clay has far bigger pores than this lower clay. Also, the total porosity seems to be a lot smaller than the actual lower clay. This is information that we haven't had before. Another interesting point is that actually the clay appears to have a higher porosity than our silt. So we see that there is a big variability in pore space between different samples, but then also throughout samples, like here where you have a lot more pores in the lower part of the sample than in the upper part of the sample. Why is this important? Well, I want you to now look closer at this sample A3. Let's see if it works. No. Okay, it should have been a video. Anyways, so what you see here is again a grayscale cube. You can see in gray the grains and then in black the pore space. And what is striking is that these pores not only are very large, but they also seem fairly horizontally aligned within the sample. This is interesting because this specific sample was taken from the upper part of the sand layer, which was previously associated with the failure plane. So previous studies have found out that the failure plane of the landslide probably formed somewhere between A2 and A3. So this horizontal alignment of the pores might have facilitated failure at this very specific location. And this is an information we can't get with any other method. So what can we learn from this case study? Well, we see considerable porosity variations between individual samples, but also within the sample itself. We've also shown that apparently the sub-centimeter changes in porosity can dictate where failure planes form. However, the method at the moment also still has quite some limitations. One, as I've mentioned during segmentation, it is hard to really only classify two classes, pores and solid phase. We have this big mixed phase. At the moment, it's a resolution limitation, but it's also an algorithm limitation. So we try to be as user independent as possible. However, when it comes to the mixed phase, a lot more input from the user is needed in order to either put it into the pore phase or the solid phase. Another problem is the actual quantification of pores. And what I mean is, I've mentioned that the pores appear elongated. In order to put a number on this elongation, we need to calculate the connectivity of pores. So to say, okay, this is an individual pore room, this is an individual pore room. However, by doing this with specific algorithms, depending on the values we use, we can either get big pores, for example, like this, but then it appears that in this case, this pore should be independent from this one. However, as the color indicates, it is connected here. If we now change the value to make sure these two are cut, well, it also cuts a lot of the other pores. So this is very user dependent, and depending on which background values and thresholds you use, your pores get smaller and smaller or bigger and bigger. And we are attempting to use new algorithms and cluster analysis to get more robust results, but at the moment, this is still work in progress. So coming already towards the end of this talk, well, the main conclusions are that, as I've mentioned, it's distinct lithological contrasts that appear to control the formation of weak layers. And it's also the sub-centimeter scale changes in sediment properties and structure that appear to control where failure is initiated. We can link specific weak layer lithologies to specific environmental settings. And we've shown that in order to really investigate weak layers, we need sediment cores. And ideally, we need sediment cores from outside the slide area and apply a multidisciplinary investigation from a very, very high resolution good seismic line to core logging and also geotechnical tasks and microcity. And I also want to point out that the integration of microcity needs to be thought through at the very beginning when you take your samples in order not to disturb your sediment core too much. And also that especially with geotechnical tests, you would usually get information over, let's say, 10 centimeters. For example, if you talk about TRIAX tests. If we talk about microcity samples, we really talk about sub-centimeter information. But it appears that the sub-centimeter information is crucial in regards to where failure planes form. And I want to end just with some ideas of future directions regarding the studies of submarine landslides and in particular weak layers, which is sampling campaigns for regions that we already know, where we have good bathymetry, where we have good seismic lines, and where we have a consistent workflow. So we can actually compare data between different case studies. And then to integrate 3D imaging techniques such as microcity imaging, as it gives us a lot more information regarding the structure of the sediment. And it can then also be integrated in numerical models. For example, you can do shear tests and run microcity at the same time, which then allows you to really image the process of the shearing and learn something about the process, which is information that is otherwise lost. I'd like to end my talk here. Thank you very much for listening. And if you have any questions, comments, I'd be very happy to hear them or write them, just read them.
Thank you for the interesting talk. So I just want to remind everybody that the chat is now open for questions. So you might want to type in your questions in the chat box and I'll read it out to you. Okay, so I have a small question. Are there any other studies that have been done to quantify the porosity and permeability, or is this again a work in progress? Okay, so porosity and permeability information has been gathered mainly from geotechnical tests. So there's a lot of engineering geology that works on that. So for example, different clays, different sands, what porosity, permeability do they have? There are data sets available. As I mentioned, the problem is that these measurements usually take up quite big samples. So you will lose information. If I talk about weak layers, often these layers are only 10 centimeters thick. So it is hard to get the geotechnical tests out of there. And we think that, but there's not a lot of microcity application yet. And we think it's the next step, basically. Okay, sure. All right. Okay, so we do have a question. They compliment you for the great talk, Hadar Elyashiv. I hope I'm pronouncing it right. So the question is it also possible to look into organic matter in the micro-CT? Did you check in the second case study you presented the sedimentation rates for the clay layers? So these are two questions.
Okay. So organic material, it's possible. We also have some organic material in our samples. However, it would be good to calibrate your scan beforehand, because organic matter can have a very similar grayscale to water, and then you will lose the information. So if it's not really siliciclastic or chalk, for example, you would have to calibrate your CT scan, but it can be done on organic matter. That's totally possible. And then the sedimentation rate, I don't have values for that, but I know it's been published. So this actual weak layer is related to a turbidity current, or the deposit of one, and a former on-land landslide. This is also where this horizontal alignment of the grains probably comes from, because it was deposited as a flow, basically.
Okay. We do not. Okay, they thank you for the answers. We do not as okay. So we do have another question by Yusdin Nichols. Thank you for the talk. Very nice work. Can you explain a bit more about why failure occurs at this specific depths in the two case studies? Base of a sand bed in Athens and near the top of the thin sand layer in the Norwegian example. Do you think that liquefaction is the primary mechanism that is responsible?
Okay. So for Athens, we really don't know yet. We think it's probably related to liquefaction. However, it's not really an earthquake-prone area. So this is still subject to debate. And we are waiting for some more samples to be taken there to really answer the question. When it comes to Finneidfjord, the background sediment makes up most of the sediment sequence there. And then you have these very prominent sequences of sand and clay. So we think that because of this little logical change, it also causes a change in the general stress regime, basically. And that's why you then focus your failure where there's already a change. So if it's similar to when you break a plate and then put it back together, it would rather break where there is already a change. And this is basically the concept of a weak layer, that due to a different lithology, you have a different setting, and then failure would focus there. And also in the case of Finneidfjord, the sand can act as an aquifer. Probably it wasn't related to an earthquake, but there was higher rainfall intensity, so it could be related to an increase in pore pressure, for example.
Okay. Let's see, we have another question too from David Gamboa. Very interesting stuff, and goes to a level of detail still lacking. And so they hope we can reach it in higher numbers. The question is, on the catalog you presented, siliciclastic sequences constituted the majority of peak failure intervals. Could you draw any considerations if sandy sequences were more prevalent than clay, or was there no relevant trend?
I actually haven't really looked into that. Interestingly, we found, so for example, in Storegga, was it Storegga? So offshore Norway, there are a few case studies where they actually talked about the difference between two clays. So a siliciclastic sequence was related to clay rather than sand and clay. And that was related to one clay being of high water content than the other one. So it really comes down to a change in physical properties in the end. But I haven't really looked into the distribution of sand and clay. I only looked into, only clay and then sand clay. But it might be something interesting to look into and see if there's a connection to also environments in the end. Yeah.
Okay. Okay, so the next question is from Khalil Al-Sanud from Morocco. Again, he thanks you for the interesting presentation. The question is, if you have recognized some soft sediment deformation structures associated with the weak layers, for example, load casts or water escape structures, so could not this be a diagnostic for the failure mechanism determination?
Unfortunately, I haven't really looked at that, mainly because I only looked at the published data, not at the sediment cores myself. So I haven't looked for soft sediment deformation, but it is something that I would expect, especially, for example, in fjords, where it's more related to clay, and also these failure planes are usually located in shallower depths. So I would expect it there more, and it might be also something I haven't really focused on in creeping landslide. So creeping landslides are not these events that initiate, within minutes, but move over long periods of time. And I would expect maybe soft sediment sedimentation, deformation, sorry, there.
Okay, good. So we have another question from Bill Arnott from Ottawa. So very nice presentation, interesting research. In the second landslide example, was the pre-slide material above or below the water table? If above, is the fluid and
it's always below.
Okay, okay. So if it's below, so I'll just read the if below part. If below, are the gas spill posed due to degassing during movement, or might they represent pre-slide trapped gas?
Okay, so I'm only talking about below sea level. In the case of the Finneidfjord slide, so there is a gas zone to the, well, it was on the right side in the image, but there's only very limited gas found in the actual sediment cores. Not enough to actually trigger a slide. However, these big pore spaces that I've shown in the microcity, due to the very round shape, I assume that they might be due to actual gas that was at least in the sediment core. And there is an interesting hypothesis that depending on how much gas you might have, it can either stabilize or destabilize a sediment sequence. If there is only a small amount of gas, it could actually stabilize it out because of the pressure. So it basically holds your sediment structure together. However, if this gas pore is then filled by water, then it loses this pressure to the outside to hold the grains, and then it might actually collapse. It's only an hypothesis, an idea I had when looking at the microcity images, that there might have been a little bit of gas that was later basically pushed out by the water, and this pushing out might have caused or helped failure, if that answered the question.
Okay, so I don't think we have any more questions. Okay, we do. So this question is from Mark from Bristol. Why is there so few slides in the southern hemisphere except the eastern coast of Australia? Is it just the lack of information?
Yeah, I think there's a sampling bias. So basically, ships go where there is economic relevance usually. You need to apply for ship time, and you need to reason why you want to do research there. So it's very often European based or the US. So there's definitely sampling bias there, and there's certainly a blind spot still. And I've actually looked for papers by specifically typing in, specific settings, and couldn't find anything. However, I might also want to point out that there might be information just not in my language, or it might not be published. That's also a big point. Often institutes gather data, it isn't published, so it just lies somewhere, and it's hard to access.
Yes. Okay, so we have another question from Jeffrey May. He's from Denver. Very interesting presentation. Can the results of your work be used to predict submarine landslides?
Unfortunately, not yet. But I'm hoping that by going further and further into characterizing the lithology of weak layers, that if we find specific lithologies that are prone to failure, we can then use it for probability maps. So if we then know about the actual stratigraphy in specific regions, we can say, okay, here's a sand layer, so the probability of failure is higher here, especially if we then add in an earthquake, for example. So I'd say it is just the basis, but I think it's something we really need if we want to increase the understanding of where failures will occur in the future.
Okay, so we have another question from Valentine, Germany. Super talk, really enjoyed it, and the quality of these figures are amazing. So based on your results, have you been approached by the Norwegian authorities for some sort of subaqueous hazard map? So can you use your results again as a predictive manner for this purpose? That's an extension of the
yeah, so I haven't. I think what they mainly focus on at the moment is bathymetry and seismics. And what I hope my work does is show that it's not enough. That yes, of course, hazard maps, the first step is a bathymetry and the seismic line. But then you need to add on the in situ and sediment core information. So I hope more people will realize that, and hopefully it will be implemented more in the future.
Okay. Well, we don't have any more questions, but there's actually a comment. Okay, so there's one more question by Bill. In the ancient sedimentary record, mass transport deposits, including slumps and slides, tend to come as discrete units separated by very little evidence of instability, even though the failed sedimentary pile may not have changed much. Do you have any thoughts on this?
Sorry, I kind of missed it. So if I may.
Okay, so the thing is, in the ancient sedimentary records for the mass transport deposits, they come as discrete units which are separated by very little evidence of instability, even though the failed sedimentary pile may not have changed much. So,
are there any thoughts on this? I don't really have an explanation for it. I mean, I think maybe if I go back to Athens, where we saw this intact sequence, which then showed some compression, for example. So it might just be that sometimes intact slabs really moved, and that's why we don't find a lot of it anymore. I think another problem, for example, I didn't include any mass transport deposits because they are very hard to link to head walls. So I'm unsure if we cannot find the information because it was never there, or because it was, you know, through afterwards the positional history lost. Yeah. So that's, I can only give my thoughts, unfortunately, that I don't really have an answer. I was wondering the same thing, and I'm hoping to find a solution of how to include mass transport deposits, because I think there's a lot that can be learned from those as well. However, I also want to point out that mass transport deposits means this material has moved. So it's hard to then really know in which material it started to move, again, because of all the erosion that goes on at the base. So I'm not sure how it can be in my specific study.
Okay.
Yeah.
All right. Okay, now I do not see any more questions.
Okay.
So I think we might conclude the event for today. So thank you everyone for joining us for this talk, and do not forget to join us next Wednesday, where we have Amy Go, who will discuss on the various data that can help reconstruct regional paleogeographies in tropical climates. See you then. Thank you all for joining.
Thank you.
Bye.